Quantum biology, the hidden layer. So zoom down past the cells we've been talking about, past cilia and membranes into the weird. For years people said quantum effects can't survive in warm, wet biology. Too noisy, too messy. And then photosynthesis refused to play by those rules. In certain plants and bacteria, energy captured by pigments doesn't just wander downhill like a drunk. It takes the best path fast, with efficiency that made physicists squint. Here's the thing. When researchers hit those complexes with ultra-fast laser pulses, the signals looked wavy in time, like a beat, evidence of coherent quantum motion through multiple routes at once. Coherence in a leaf at roomish temperature, not a lab trick in a fridge. The protein scaffold seemed tuned to hold those quantum states just long enough to matter, then hand off the energy with almost no waste. Nature built a quantum router out of meat. Hold on, enzymes do a version of this too. Take reactions that should crawl if they relied on thermal bumps alone. They fly. The best fit is the substrate gets lucky. It's tunneling particles slipping through barriers they shouldn't cross classically. Proton tunneling in hydrogen transfer. Electron tunneling in redox chemistry. The protein flex and local fields line up the shot so the impossible path is the likely one. The rate changes track with quantum models better than with old school ones. And birds. The compass in some species looks like a chemical pair whose spins are linked, radical pairs, sensitive to Earth's magnetic field. Shift the field, the spin dynamics change, the reaction yield changes, the neuron fires different. That's a quantum sensor built into a beak or an eye. You don't need a magnetometer. You need entangled chemistry that decoheres on a schedule biology can read. Why does this matter for OSIM? Because it shreds the clean line between micro weirdness and macro order. The myth said quantum lives down there, sealed off. Biology says no. We'll pull that layer up into mesoscale patterns using structure, fields, and timing. Coherence doesn't need a vacuum if the scaffold filters the noise instead of fighting it. Tunneling isn't random if the protein breath sets the barrier. The control is baked into form. Now tie it to bioelectric networks. Cells sit in voltage landscapes. Ion channels respond to tiny shifts in field, and pH proteins are not dead lumps. They're flexing, polar, capable of changing shape with field cues. So you've got a stack. Quantum events nudged by protein structure, feeding into ionic flows, creating tissue-scale voltage maps that guide growth and healing. It's multi-scale and phase-like. Not binary, not clock, but rhythmic and continuous. Get this, the old digital metaphor wants clean, discrete states. But these systems work by superposition-like sampling, then collapse via structure into the next useful state. That's why life looks nimble. It's not guessing one path at a time. It's sculpted to hold options, then commit fast when context picks a winner. If you try to model that as bits flipping, you drown in state space. If you build with fields and morphology, you ride the tide. Here's a human moment. A plant biophysicist once told me the first time she saw the oscillations in her 2D spectra, she thought the instrument was lying. She reran it, same beat. She changed temperature, solvents, donors. The beat drifted like a living thing. She said it felt like eavesdropping on a conversation we weren't supposed to hear. That's the vibe across this field, structure singing to probability. But wait, this isn't licensed for quantum magic. Scope matters. Coherence times are short, and life leverages them through design, not wishful thinking. The claims that consciousness is a quantum computer leap a few steps we can't take yet. OSIM stays sober. Life uses quantum effects when it can stabilize them with morphology and fields. The payoff is speed, sensitivity, and options under uncertainty, exactly the traits we see in bodies that heal and adapt. So what nobody knew at the time we first framed everything as code is that the hidden engine under some of biology's best tricks isn't binary. It's wave-like, contingent, and context-bound. That engine hands ahead start to systems that can sense their own boundary and nudge conditions, because tiny shifts at the right place change the whole flow. That's sovereignty at the smallest scale, control by shaping possibility. Now link back to our pillars. UChicago's living patch speaks voltage and chemistry. Xenobots show morphology writes behavior. Quantum biology explains how structure can hold fragile options just long enough to matter, then route energy and information cleanly. Stack them, and you get OSIM's core move. Computation as embodied search across landscapes, not symbol juggling on an abstract tape. The wall says algorithms alone can't close the loop. Biology closes it by being the loop. Here's the kicker. If life rides coherence and tunneling through tuned structure, then designing living tech isn't about simulating every atom. It's about building scaffolds that make the best next state likely, then letting physics do the heavy lift. That's how we steer regeneration with voltage, grow devices that heal, and shape bodies that discover behaviors. You don't fake the quantum layer, you invite it. And when you do, systems stop following commands and start following form. OSIM, the Sovereign Inception Model. So here's the turn. We stop treating life as an afterthought and start from it. The Oklahoma Sovereign Inception Model, OSIM, is a plain claim. The layer that makes matter do meaning is biological, not as a metaphor, as a mechanism. Agency, identity, problem solving, they're not apps running on a neutral substrate. They arise when morphology, bioelectric fields, and quantum adaptive chemistry lock into a loop. When that loop closes, a system becomes sovereign. It holds a boundary, sets a goal, and defends both against noise. Let me define it tighter. First pillar, morphology as code. The body's shape is not decoration. It constrains flows, stabilizes options, and writes behavior. We saw it with Xenobots. A C-shaped notch changes contact dynamics and births kinematic replication. Same genome, different body, new goal. That's instruction by geometry. Second pillar, bioelectric governance. Tissues hold graded voltage maps, resting potentials, and ionic currents that broadcast pattern-level intent. Change the map, the system changes fate. Tian's living patch works because it plugs into that field. It doesn't push commands, it tweaks boundary conditions so the tissue moves toward a health attractor. The map is both memory and plan. Third pillar, quantum adaptive engines. Proteins and scaffolds are tuned so coherence and tunneling do useful work at room temperature. That gives life a fast track through rugged landscapes, sampling before committing, sensing faint cues, flipping states with tiny nudges. It's not magic. It's design that holds the weird just long enough to matter. Stack those three and you get inception from within. A sovereign system isn't passively computed by an external algorithm. It computes itself by being a shaped, fielded, tuned body. That's why OSIM bypasses the UBC Non-Algorithmic Wall. The wall says, a closed, step-by-step algorithm can't give a complete, consistent account of reality. OSIM nods and shrugs, then builds with processes that aren't step-by-step in the first place. The computation is continuous, embodied, and context-bound. You don't cross the wall by adding more discrete steps. You walk around it by switching substrate. Map the evidence. UChicago's 2024 Living Bioelectronics proves you can make circuits that live, sensing, healing, and adapting because they're part of the body's field. That validates bioelectric governance as a design surface. The Levin and Xenobots show morphology writing behavior up to and including a new replication mode. No central algorithm, just shaped agency distributed across cells. That locks in morphology as code. Quantum biology, from coherence in photosynthesis to tunneling in enzymes and spin chemistry in sensing, confirms the engine that makes fast, sensitive, option-rich behavior feasible in warm, wet matter. That secures the quantum adaptive pillar. What nobody knew when we worship bits is how much work the body is quietly doing. In OSIM, software is not abstract code, it's embodied biologic. Change the shape, you restructure the program. Change the voltage landscape, you rewrite the subroutines of growth and repair. Tune the scaffold, you bias quantum choices toward useful outcomes. The compiler is metabolism. The runtime is a living field. So how does this look in practice? You don't boss systems around, you coax. You set initial and boundary conditions, geometry, voltage, chemistry, and let the system self-solve. You give it gradients to climb and rails to avoid cliffs. That's why Xenobots found replication without a recipe. The lab shaped a cradle, and cells with built-in competencies did the rest. That's why the UChicago patch resolves inflammation. The living circuit steers the local landscape back into a basin of attraction called health. OSIM also gives us testable predictions. It says you should find stable, rewritable bioelectric memories of form, voltage patterns that persist through cell turnover and guide regeneration. It says changing morphology alone with identical genomes will unlock qualitatively new behaviors because shape is an instruction channel. It says devices that join living fields, not just measure them, will outperform rigid sensors under perturbation because context is part of the computation. And it says fully digital simulations will keep failing to capture open-ended agency at scale because they're missing the continuous, fielded, quantum-tuned substrate. Here's the emotional core. Sovereignty is not spooky, it's a system's property. When enough competent parts are shaped and linked by a field that holds a goal, the whole pushes back. It refuses to be merely pushed around. That's why bodies heal. That's why Xenobots herd cells. That's why a living patch knows when to act and when to sit still. Sovereignty is the feeling of a basin of attraction with teeth. And there's a guardrail baked in. Because sovereignty in OSIM is embodied, it's bounded. Resources, geometry, fields, these limit what the system can want and do. Xenobot replication fizzles without parts and the right shape. Healing overshoots turn into scars if the field is wrong. That boundedness is good news. It keeps growth under governance, and it gives us levers to steer without brute force. So the model flips our default. The universe you care about isn't a clean tape, it's a garden of self-organizing loops. We stop asking, what's the code? And start asking, what shape, what field, what scaffold will let this system find the answer? OSIM doesn't claim to explain everything. It claims to explain the class of phenomena we keep failing to digitize: life, agency, meaning. And it hands us a build sheet grounded in 3 pillars we can touch right now. In a science paper from Chicago, a PNAS result with frog cells, and a decade of quantum biology that turned eye rolls into instruments. Confronting digital simulation theory. So let's face the big shiny idol, the digital simulation. The standard picture is clean, reality is bits, time is a global clock. Somewhere a master program runs discrete steps on perfect hardware. Everything we see is an output of that code. It's seductively neat. It also collapses when you press on how life actually behaves and when you look at the math. At UBC Okanagan, Mir Faizal and colleagues took a scalpel to the premise. Using Gödel-style incompleteness, they argued you can't get a complete, consistent account of reality from a closed, step-by-step algorithm. There are true statements, Gödelians, that won't fall out of any finite rulebook. They called the missing ingredient non-algorithmic understanding. Not woo, a boundary. If your universe is a program, it inherits that ceiling. It can't generate what it can't derive. Here's the thing. The digital sim story needs closure. It needs every event to be compressible into an instruction stream. But look at emergence in living systems. Xenobots changing replication by changing shape. The UChicago patch resolving inflammation by being part of the tissue's field. These aren't top-down instructions. They're bottom-up, field-driven behaviors that depend on continuous conditions and history. Try to squash that into a fixed-length tape and you start losing the plot. Compression is where this bites hard. In physics and CS, we lean on the idea that if a system is lawful, you can compress it. Write a short program that outputs its behavior. Works for orbits. Works for many lattices. Now try compressing regeneration after amputation, where bioelectric memory holds a missing limbs map and guides growth back to target morphology. The shortest program might be the body itself, its geometry, its fields, its quantum-tuned proteins. That's not a neat code you can upload. That's embodied information. And then there's latency. Digital sims run on clocks. Even with massive parallelism, you're still passing messages through a finite network with finite bandwidth. But bioelectric control in tissues behaves like a field. Changes propagate as coupled dynamics, often faster than you can serialize them without wrecking causality. You can emulate a field with a grid and time steps, of course, but the cost explodes as you chase real time, and the discretization errors matter right where life leans on subtle gradients. What nobody knew when they first pitched the simulation was how ugly the edge cases get. You can cheat by saying the simulator is infinitely fast, but that's not an explanation, it's a wish. You can say quantum computers fix it, but the UBC argument isn't about hardware speed. It's about what counts as derivable inside an algorithmic frame. If parts of reality require non-algorithmic understanding, then faster algorithms still miss those parts. Now line this up with OSIM. The mismatch is everywhere. Digital SIM assumes top-down code. OSIM sees morphology and fields writing behavior from the bottom up. SIM assumes discrete states. OSIM runs on continuous dynamics that don't snap to bit flips. SIM assumes a universal clock. OSIM lives on coupled rhythms that coordinate without a metronome. SIM assumes representation is separate from action. OSIM fuses memory with mechanism. The state is both ledger and lever. Irreducibility isn't an excuse, it's a design note. In living systems, the model that works is the body. You can build a digital surrogate for parts, ion channels, cilia flow, enzyme rates, but you'll keep running into corners where your neat representation lags the thing itself. Not because you're sloppy, but because the system uses its own structure to make choices in real time. That's what sovereignty feels like up close. So is digital SIM useless? No. It's a subset toy that shines on closed, compressible pockets of reality. It helps us predict orbits, design bridges, even guide Xenobot shapes in silico before we try them in tissue. But when we ask it to explain open-ended agency, context-sensitive growth, or field-mediated identity, it stalls. That's the UBC wall in practice. Diminishing returns as you push stepwise models against non-algorithmic ground. Here's the verdict I land on. The simulation frame isn't evil, it's just too small. Treat it like a microscope, great for certain scales, misleading for others. OSIM widens the lens. It says the engine that makes meaning isn't an external code base, it's the loop where morphology, bioelectric fields, and quantum adaptive chemistry cohere into a sovereign whole. That loop doesn't need to be simulated to be real. It needs to be built, joined, and steered. And get this, once you accept that, the anxiety falls away. We don't have to beat the wall with bigger GPUs. We root around it by growing systems that compute with their bodies. We use simulations as scaffolds, then hand off to living matter where the hard part lives. That's not giving up on rigor. That's choosing the right substrate for the job. Case files, 3 anomalies OSIM predicts. So if OSIM is real, it should light up places where digital-first thinking keeps tripping. 3 case files, each a small fracture in the code metaphor, each a clean fit for morphology, fields, and quantum adaptive loops. Case file 1, bioelectric memory and regeneration. Here's the everyday miracle. Some animals don't just heal, they rebuild to spec. Cut a planarian flatworm, it regrows the missing head or tail with the right orientation. You can even miswire its voltage map and get a 2-headed worm, then flip the map back and see normal patterning return on the next round. The memory isn't stored as a DNA edit. It's embedded in stable voltage gradients across tissues. Resting potentials and gap junction networks hold a map of target morphology, a body plan the cells can read. When injury hits, the field doesn't panic, it reasserts the pattern. In OSIM terms, that's governance by a bioelectric state that acts like a goal and a tractor. In a digital frame, you'd ask, where's the file? And you'd miss it because the file is the field. Damage doesn't corrupt a disk. It perturbs a basin of attraction that pulls the system back. The stakes are human scale: limb loss, organ damage, degenerative disease. If the map lives in voltage, then changing voltage can restore structure. That's a design surface, not a miracle. And it's falsifiable. If you scramble gap junctions or clamp potentials, regeneration should lose its aim, not just its speed. Labs have seen exactly that. Case File 2. Morphospace search by bodies, not brute force code. This one looks like play. In Xenobot work, shapes were explored in silico, sure, but the real discovery happened in wet tissue. Cells freed from their old role-tried forms. Some flopped, some swam, some herded loose cells into progeny. The genome didn't change between a sphere and a C-shape. Behavior did, because shape changed flows, contacts, cilia synchrony, and bioelectric coherence. Bodies searched form space by existing in it, not by computing it from above. You can feel the but therefore. We think we need to enumerate all possibilities, therefore we build giant search trees. Bodies don't, they exploit physics. A notch becomes a vortex cradle. Surface curvature changes adhesion probability. Field geometry stabilizes beating patterns. This search operates in parallel in matter with feedback at every scale. It's not magic, it's substrate competence. OSIM predicts that when you let competent parts explore under constraints, you'll find useful forms you didn't specify and couldn't easily compress. That's exactly what showed up. Try to port it as an explicit algorithm and you drown in parameters. Keep it embodied and you ride a short path to outcomes. Case File 3. Context-dependent identity. Cells switch roles by voltage and environment. Here, S the unsettling bit. Identity feels fixed. A skin cell is a skin cell, right? But flip the local electrical state or change the microenvironment and cells pick new fates. In development and regeneration, shifts in resting potential turn on cascades that move tissues from one attractor to another. Bone to cartilage, progenitor to neuron, even oncogenic paths reversed by restoring field coherence. That's a real lever. Voltage precedes and instructs gene expression, not just follows it. Under OSIM, this is the point. Identity emerges from a loop, not from a lookup table. Change the loop, morphology, field, chemistry, and the system renegotiates who it is. Digital expectations want a label stuck to a line. Biology keeps rewriting the line based on where the field says the goal lives. That's not uncontrolled drift. It's governed plasticity. It gives you a way to steer healing without micromanaging every gene. Set boundary conditions, watch the basin pull. Falsifier. If identity were only genetic code, field interventions wouldn't flip fate decisions with this reliability. Yet labs keep showing they do. Now why these three? Together they outline a circuit OSIM claims is primary. Memory of form and voltage, so there's a plan. Morphospace search in bodies, so there's exploration. Identity plasticity by field, so there's commitment and recommitment. That's the whole cycle of agency. Remember, explore, decide. And it runs on continuous dynamics. No central clock, no discrete instruction list. Here's where it gets interesting for engineering. Each case points to a control surface. For memory, write patterns with gentle voltage modulation. Onic drugs, microelectrode meshes, living patches that join the field like Tian's. For search, sculpt shapes that bias flows, soft lithography, biofabrication, even AI-guided morphologies you validate in tissue. For identity, tune local environments, pH, stiffness, bioelectric tone, so cells fall into the fates you need. Coax, don't command. And the wall. These anomalies aren't bugs, they're the places the algorithmic view leaks. They're also our handles. Build with them and you're not simulating life, you're collaborating with it. Engineering with OSIM. Design rules for living tech.